History of Java. Java was developed by James Gosling at Sun Microsystems and released in 1995 as a core component of Sun Microsystems' Java platform. It was originally designed for interactive television, but it was too advanced for the digital cable television industry at the time. The language was initially called Oak, after an oak tree that stood outside Gosling's office, and then was renamed to Java, from Java coffee, a type of coffee from Indonesia. Let's take a simplistic approach to emulate how a Java version display might look in a Java program. This simple Java code embodies a basic program structure in Java. The public class Java History declares a class named Java History. In Java, every application begins with a class definition. Inside the class, we have the main method, which is the entry point of any Java application. The statement system.out.println. Java was created in 1995 by James Gosling and Sun Microsystems. Inside the main method is used to print the statement to the console, providing a simple illustration of outputting text in Java. This piece of code, though basic, reflects the essence of writing and executing Java programs, serving as a practical tribute to Java's creation history. Features of Java. Java is a widely used programming language designed with simplicity, portability, and user-friendliness in mind. Let's go through some of its key features that make it a popular choice among developers. 1. Simple. Java's syntax is clean and easy to understand, making it an excellent choice for beginners. 2. Object-oriented. Everything in Java is treated as an object, which helps in making applications modular, flexible, and extensible. 3. Portable. Java code can run on any device that has the Java Virtual Machine, JVM, enabling the write once, run anywhere, WARA capability. 4. Secure. It provides a secure environment by avoiding explicit pointer and running programs inside the JVM. 5. Multi-threaded. Java supports multi-threaded programming, which allows you to perform many tasks simultaneously within a single program. The given code demonstrates a basic Java program, printing Hello World. On the console, showcasing how Java's syntax is both simple and efficient. JDK, JRE, and JVM. Understanding the Java Development Kit, JDK, Java Runtime Environment, JRE, and Java Virtual Machine, JVM, is foundational to starting with Java. They are the core components that allow developers to create and run Java applications. JDK, Java Development Kit, is a software development kit required to develop Java applications. It includes the JRE, Java Runtime Environment, compilers, and tools like JavaSac for compiling Java code. The JRE provides libraries, the JVM, Java Virtual Machine, and other components to run applications written in Java. The JVM is the engine that executes Java bytecode, providing a platform-independent way of running Java applications. For instance, the provided code snippet Hello World would be compiled by the JDK's compiler, JavaSac, into bytecode, which is then run on the JVM. The JRE's libraries are utilized by the application at runtime. Writing your first Java program. Writing your first Java program is an exciting step into the world of programming. Java programs are written in a text file with a .java extension. The program then needs to be compiled into bytecode by the Java compiler, and this bytecode can be executed by the Java Virtual Machine, JVM. The simplest Java program you can write is one that prints a message to the console. Let's take a look at how this is done. The code provided is a basic Java program that outputs Hello Java to the console. Public class Hello Java defines a class named Hello Java. In Java, each application must contain a main method, which is the entry point for the program. Public static void main string args declares this main method. It must be public, accessible from anywhere. Static doesn't need an instance of the class to be invoked, and it returns no value, void. String args is an array that stores command line arguments. System.out.println, hello, Java, uses the system class from the Java standard library to print the specified string to the console. This is a straightforward example, but it includes several key concepts in Java programming. Understanding the structure of a Java program. Every Java program follows a basic structure for execution. This structure includes, at a minimum, a class declaration, the main method, and statements within the main method. Let's explore this through a simple example. 1. Public class Hello World. This line starts the declaration of a class named Hello World. Every Java application must have at least one class definition that matches the file name. 2. Public static void main string args. This line signifies the main method, which is the entry point of any Java application. The Java runtime executes this method upon launching the program. 3. System.out.println hello world. Within the main method, this line is a statement that prints the text hello world to the console. Statements may include expressions, control flow statements, or method calls. Overall, this basic structure is necessary for every Java application, providing a framework for the execution of your program. Compilation and execution process. In Java, the process of converting your code into a format that can be executed by the Java Virtual Machine, JVM, involves two main steps: compilation and execution. First, the Java compiler transforms source code into bytecode using the Java command. Then, the Java Virtual Machine JVM executes this bytecode using the Java command. Let's go through a simple example demonstrating this process. First, the helloworld.java source file is compiled by running java helloworld.java, resulting in a helloworld.class file containing bytecode. This bytecode is a platform-independent code that can be executed on any device equipped with a JVM. Finally, the bytecode is executed with Java Hello World, which starts the JVM, loads the Hello World class, and calls the main method. The main method then executes, printing Hello World to the console. This two-step process, the compilation to bytecode and the subsequent execution by the JVM, enables Java's write once, run anywhere capability. Data types. In Java, data types specify the size and type of values that can be stored in variables. Java has two categories of data types: primitive, which includes byte, short, int, long, float, double, boolean, and char, and non-primitive, which includes classes, interfaces, and arrays. Here we'll concentrate on primitive data types. In this code, we define a class datatypesDemo with a main method that creates variables of different primitive data types. Int is an integer data type that stores whole numbers. Float stores decimal numbers, but requires an f at the end to indicate it's a float. Char represents a single character and requires single quotes. Boolean can hold true or false values. The system.out.println statements print the values of these variables to the console. Variables. In Java, a variable is a container that holds data which can be changed during the execution of a program. Each variable has a specific type, which determines the size and layout of the variable's memory, the range of values that can be stored, and the set of operations that can be applied to the variable. In this code snippet, we declare two variables. The first line, int myNumber equals 10, declares an integer variable named myNumber and initializes it with the value 10. The type int indicates that this variable can hold integer values. The second line, string myString equals hello world, declares a string variable named myString and initializes it with the value hello world. The type string indicates that this variable can hold sequences of characters, making it suitable for text. The equals symbol is used to assign values to the variables during their declaration. Operators. In Java, operators are special symbols that perform operations on variables and values. Operators can be used to perform arithmetic operations, compare values, or manipulate logical conditions. Here, we'll focus on the arithmetic operators that allow you to perform basic mathematical operations such as addition, subtraction, multiplication, and division. The example code demonstrates the use of basic arithmetic operators in Java. The plus operator is used for addition, resulting in the sum of a and b. The minus operator is used for subtraction, yielding the difference between a and b. The store operator is used for multiplication, giving the product of a and b. Lastly, the slash operator is used for division, resulting in the quotient of a divided by b. This code illustrates how operators can modify values and produce a new result, which is then printed to the console. Expressions, statements, and blocks. In Java, expressions, statements, and blocks are fundamental building blocks of a program. An expression is a construct made of variables, operators, and method invocations that evaluates to a single value. Statements are the instructions given to the computer to perform, which often contain expressions. Blocks are groups of 0 or more statements enclosed in braces, used to define a scope. In the provided code 10 plus 5, is an expression that evaluates to the value 15, which is then assigned to the variable result. This assignment itself is a statement, specifically an expression statement. The if construct represents a statement that checks if result is greater than 10. Inside the braces is a block that contains another statement, a call to system.out.println, which outputs a string if the condition is true. This example demonstrates how expressions, statements, and blocks can be used together in Java to perform operations and control the program's flow. Control flow statements: if, if-else, switch, loops. Control flow statements in Java help you to make decisions using if, if-else statements, choose between a block of code out of multiple blocks using switch statement, or execute a block of code multiple times using loops like for, while, and do while. These are fundamental in giving your application the ability to make decisions and perform repetitive tasks. This code snippet demonstrates the use of if-else statements. It checks if a number is greater than 0, less than 0, or exactly 0, and then prints a corresponding message to the console. The flow goes into the first true condition encountered and skips the rest. This way of decision-making allows the program to execute different code blocks based on varying conditions. Comments in Java. In Java, comments are annotations in the source code that are ignored by the compiler. They're used to explain what the code does, making it easier to understand for whoever reads it. Java supports 3 types of comments: single-line, multi-line, and documentation comments. The single-line comment starts with slash and extends to the end of the line. The multi-line comment starts with /* and ends with stars and can span multiple lines. Documentation comments, which start with // and end with thus, are used by the Javadoc tool to generate documentation. They can contain HTML tags and Javadoc tags to produce rich documentation. Introduction to OOP. Object-oriented programming, OOP, is a programming paradigm based on the concept of objects, which can contain data in the form of fields, often known as attributes or properties, and code, in the form of procedures, often known as methods. Java is inherently object-oriented, meaning everything in Java is associated with classes and objects. Let's look at a simple example of a class and how it can instantiate an object. This code snippet demonstrates the basics of OOP in Java. A car class is defined with one attribute, color, a constructor to assign a value to color when a new car object is created, and a method, displayColor, which prints the car's color to the console. The main class contains the main method, which is the entry point for any Java application. Inside it, a new object of the car class is created with red as its color, and its displayColor method is called to display the color of the car is red. Through this simple example, we see how Java utilizes classes and objects to encapsulate and manipulate data. Classes and objects. In Java, the foundation of object-oriented programming includes classes and objects. A class is a blueprint from which individual objects are created. It defines a particular kind of data structure that encapsulates data, attributes or properties, and methods, functions or subroutines that operate on the data. An object is an instance of a class created with specific data. Let's look at a simple example to understand these concepts better. In this code snippet, car is defined as a class with 2 attributes, color and model, and a method, displayInfo, that prints out the car's details. The main class contains the main method where we create an object myCar of the class car. We then assign values to the attributes of myCar, red for color and Tesla Model S for model, and call the displayInfo method to display these values. This demonstrates how classes serve as blueprints for objects, which are instantiated with specific attributes and behaviors. Methods, declaration, and invocation. In Java, methods are blocks of code designed to perform a specific task. A method is declared within a class, and it's invoked to execute the task when needed. Method declaration involves specifying the method's return type, name, and parameters, if any. Invocation is calling the method to execute. Let's examine a simple example to understand how to declare and invoke a method in Java. In the above code, we declare and invoke a method within the calculator class. The add method is declared with public static int, which indicates that it is a public method accessible from outside the class. Static called without creating an instance of the class, and int returns an integer. It takes two integer parameters. Within the main method, we invoke the add method by passing two integers, 10 and 20, as arguments. The method computes the sum and returns it. The returned value is then stored in the variable sum and printed out. This demonstrates the basic principle of method declaration and invocation in Java. Constructors. Constructors in Java are special methods used to initialize new objects. They are called when an instance of a class is created. Constructors have the same name as the class and do not have a return type, not even void. Java provides a default constructor if you don't define any, but as soon as you define your own constructor, the default one is not available. This code defines a car class with two instance variables, model year and model name. The car class has a constructor that takes two parameters, an integer, year, and a string, name, which are used to initialize the model year and model name variables, respectively. In the main method, a new car object named myCar is created by calling the car constructor with the year 1969 and the name Mustang. Finally, the model year and model name of myCar are printed to the console. This keyword. In Java, this is a reference variable that refers to the current object. It is used to refer to the class instance variables, constructors, or methods. This keyword resolves the ambiguity between class attributes and parameters with the same name. It's also used to pass the current object as a parameter to another method or constructor. Let's see this keyword in action to understand its usage better. In the provided code, the this keyword is used in the constructor car string make string model. Here, this.make and this model refer to the instance variables of the car class, while make and model refer to the constructor parameters. Without this, the compiler would not be able to distinguish between the instance variables and parameters since they have the same names. The this keyword eliminates this ambiguity by explicitly stating that the scope of this.make and this.model is the current object. Furthermore, this is used in the display method to refer to the current object's variables, although it's not strictly necessary in this context, since there's no local variable with the same name. However, it's a good practice to use this for clarity and consistency. Inheritance. In Java, inheritance is a mechanism where one class acquires the properties and behaviors of another class. This concept helps to create a hierarchical classification. The class which inherits the properties of another class is called the subclass or child class, and the class whose properties are inherited is known as the superclass or parent class. In the provided code, animal is a superclass with the method eat. Dog is a subclass of animal, and it inherits the eat method from animal, meaning it can perform the eat action without having a separate eat method within its class. Additionally, dog has its own method bark. In the test inheritance class, a dog object is created, and both eat and bark methods are called. This demonstrates how dog can use methods inherited from animal alongside its own methods. Polymorphism. Polymorphism, in the context of object-oriented programming, refers to the ability of different classes to respond to the same method call in different ways. It allows objects of different classes to be treated as objects of a common superclass. There are two main types of polymorphism: compile time, method overloading, and runtime, method overriding. Here, we'll focus on runtime polymorphism with an example using method overriding. In this example, we've defined a superclass animal with a method speak. The dog class extends animal and overrides the speak method with its own implementation. In the test polymorphism class, we create a dog object, but reference it with an animal type. When we call the speak method on this object, Java runtime determines the actual object type, dog, and executes the overridden speak method in the dog class. This demonstrates runtime polymorphism, where the decision about which method to execute is made at runtime. Abstraction. In Java, abstraction is the concept of hiding the complex implementation details and showing only the necessary features of an object to the outside world. It is achieved using abstract classes and interfaces. An abstract class cannot be instantiated, but they can have abstract methods, methods without body, and concrete methods, methods with an implementation. Let's look at a simple example to understand how abstraction works in Java. In the provided code, animal is an abstract class with an abstract method, makeSound, and a concrete method, eat. The abstract method, makeSound, does not have an implementation in the animal class. It's a way to force the subclasses to provide their own implementation of this method. The dog class extends animal and provides its own implementation of the makeSound method, printing bark to the console. The test abstraction class demonstrates using these classes. An instance of dog is created as an animal type, and we call both the makeSound and eat methods on it. This illustrates abstraction by hiding the implementation details of how different animals make sounds, and only exposing the actions that an animal can perform. Encapsulation. Encapsulation is a fundamental concept in object-oriented programming that involves bundling the data, attributes, and code acting on the data, methods, together as a single unit. It also restricts direct access to some of an object's components, which is a way of preventing accidental modification or misuse of data. This is typically achieved through the use of access modifiers. Let's look at a simple example. In this code, the student class has two private fields, name and age. Private fields are not accessible outside their class, which is a key aspect of encapsulation. By being private, we ensure that these fields cannot be directly accessed or modified from outside the student class, thus safeguarding the data integrity. To provide controlled access to these fields, public getter and setter methods are defined: getName, setName, getAge, and setAge. The setName method allows setting a new name, and getName returns the current name. Similarly, setAge updates the age if it's a positive number, while getAge returns the current age. This design pattern allows for controlled access to the internal state of the student object, thus protecting the integrity of the data. Interfaces. In Java, an interface is a reference type, similar to a class, that can contain only constants, method signatures, default methods, and static methods. Interfaces cannot contain instance fields or constructor methods. An interface is used to specify a set of methods that a class must implement. Interfaces are a way to achieve abstraction and multiple inheritance in Java. In this example, animal is an interface that contains a single method, eat. The dog class implements the animal interface and provides an implementation of the eat method. In the main method of the test interface class, we create an instance of dog, but reference it with animal type. When eat is called on this reference, it executes the eat method defined in the dog class, displaying dog is eating. This demonstrates how interfaces can be used to achieve abstraction by not specifying how a method should be implemented, but rather just that it must be implemented. Packages. In Java, packages are used to group related classes and interfaces together. This organization helps in code management, prevents naming conflicts, and controls access with proper encapsulation. A package can be built in, like java.util or user-defined. Let's see a simple example of how to create and use a custom package. In the example, package myPackage declares that myPackage class is part of the package named myPackage. To use myPackage class in other classes, you must import this package using import myPackage class. This is necessary unless the classes are in the same package. The myPackage class contains a method display that prints a message to demonstrate its function. TestPackage class imports myPackage class and uses it, showing the encapsulation and organization provided by packages. Arrays, declaration, creation, and initialization. In Java, arrays are used to store multiple values of the same type in a single variable, instead of declaring separate variables for each value. To use an array, you typically follow these steps: declaration, creation, and initialization. In the declaration phase, int myArray, you define the array and its element type. Here, myArray is an array that will hold int values. Creation, myArray equals new int 5, allocates memory for 5 integers in myArray. During initialization, myArray 0 equals 10, myArray 1 equals 20. Individual array elements are assigned values. The first element, myArray 0, is set to 10, and the second, myArray 1, to 20. Array indices start at 0. Multi-dimensional arrays. In Java, a multi-dimensional array is essentially an array of arrays. The most common type is the two-dimensional array, which is often used to represent matrices, tables, or any structure that requires row and column organization. A two-dimensional array can be declared, instantiated, and initialized using both single and multi-dimensional views. Let's dive into an example where we initialize and access elements from a two-dimensional array. In this example, int matrix declares a two-dimensional array of integers. The array is then initialized with 3 rows and 3 columns, where each row is an array itself, containing 3 elements. The notation 2 in matrix 1, 2 refers to accessing the element in the second row because indexing starts at 0 and third column of the matrix. The printed result is 6, which is the value located at that specific row and column in our multidimensional array. Notice how we work with indices, remembering that they are 0-based, which means counting starts from 0 rather than 1. String class and its methods. The string class in Java is used for storing and manipulating sequences of characters. It offers a wide range of methods to perform different operations like comparing, concatenating, converting, trimming, and splitting strings, among others. Let's explore a few commonly used string methods. The example demonstrates several string methods. Str.length returns the length of the string. Str.char@7 returns the character at index 7 of the string. Str.sub712 extracts a part of the string starting from index 7 to index 12, excluding 12. Str.to lowercase converts all characters in the string to lowercase. Similarly, to uppercase converts them to uppercase. Str.replace world Java replaces the word world with Java in the string. These methods highlight the immutability of strings in Java, meaning original strings remain unchanged, and operations return new string instances. String buffer and string builder classes. In Java, string objects are immutable. This means once a string is created, it cannot be changed. This can lead to performance issues when you have to modify a string repeatedly, e.g., in a loop. Java provides 2 classes to overcome this issue: string buffer and string builder. Both classes allow you to create mutable strings. The main difference between them is that string buffer is thread-safe and synchronized, which makes it slower, whereas string builder is not thread-safe but faster. They are ideal for scenarios where you need to manipulate the contents of a string, such as appending, inserting, or reversing the string. In the provided code, we first create a string builder object, SB, with the string hello. Using the .append method, we then add world to it. When we print SB, it displays hello world as string builder modifies the original object instead of creating a new one. Similarly, we create a string buffer object, SBF, with the string start and append end using the .append method. The SBF object now contains start end. Both examples illustrate how you can modify strings without creating new objects each time, thus improving performance, especially in scenarios that involve frequent modifications to the string. Commonly used string methods. In Java, the string class provides a lot of methods to perform operations on strings. Let's explore some of the most commonly used methods, such as length, char@, substring, index of, and to lowercase. Understanding these methods will help you efficiently manage and manipulate strings in your Java applications. This code demonstrates the usage of commonly used string methods. The method length returns the length of the string. Char@, int index, returns the character at the specified index. Substring, int begin index, int end index, returns a new string that is a substring of the given string. Index of int ch returns the index within this string of the first occurrence of the specified character. Lastly, to lowercase converts all the characters in the string to lowercase. Together, these methods provide a powerful toolkit for string manipulation in Java. Basics of Collections Framework. The Collections Framework in Java provides a unified architecture for representing and manipulating collections, allowing them to be manipulated independently of implementation details. It includes interfaces like list, set, and map, and classes like ArrayList, HashSet, and HashMap. This code snippet demonstrates the basic use of the Collections Framework. Here we import the ArrayList and list from the java.util package. We then create an instance of list string named fruits, and initialize it with an instance of ArrayList. This setup allows us to add elements to fruits using the add method. Finally, we print the contents of fruits, showcasing how a collection can store and manage groups of objects. This basic example outlines how to work with the collections framework, showing its simplicity and power in managing groups of objects together. List, map, set. A list in Java is an ordered collection that can contain duplicate elements. It maintains the insertion order, allowing positional access and insertion of elements. Lists are part of the Java collections framework and can be instantiated using classes such as ArrayList and LinkedList. In this code snippet, we create an array list named fruits that stores elements of type string. We add 3 elements to the list: apple, banana, and cherry. Finally, we print the list to the console, which will display the elements in the insertion order: apple, banana, cherry. ArrayList and LinkedList. ArrayList is a part of Java's collection framework that acts like a dynamic array. Unlike arrays, it can automatically resize itself when elements are added or removed. It maintains insertion order and allows duplicate elements. Here's a simple example to demonstrate basic operations like adding, removing, and accessing elements. In the provided code, we import the ArrayList class and create an instance of it called fruits. We then add 3 elements to the list. The get method is used to access the element at index 1, which prints banana. Later, we remove banana from the list using the remove method. Finally, printing fruits displays the current list contents, showing apple and cherry after the removal. Hash set and tree set. Hash set is a collection that contains no duplicate elements and does not maintain any order. It's backed by a hash table, ensuring constant time performance for basic operations if the hash function disperses elements properly. Here's how to use a hash set in Java. In the provided code, a hash set named fruits is created to store string elements. We attempt to add apple, banana, and apple again to the set. Hash set does not allow duplicates, so the second attempt to add apple is ignored. When printing the set, you will see that it only contains unique elements. Note, the order of elements might not reflect the order of insertion due to the nature of hash set. Hash map and tree map. Hash map in Java is part of the collections framework. It stores items in key-value pairs, allowing quick access and manipulation of data. Keys must be unique, but values can be duplicated. It does not maintain any order of the elements. In the provided code, a hash map is created with integer keys and string values. The put method is used to insert 3 key-value pairs into the map. To retrieve an item, the get method is called with the key, e.g. map.get1 returns apple. Note that the order in which elements are inserted is not preserved in the output. Iterators and list iterators. The iterator interface provides a way to traverse through a collection sequentially without needing to understand the underlying structure of the collection. It has methods like hasNext, next, and remove. In this example, an array list named animals is created and populated with several strings. An iterator, it, is then created by calling animals.iterator. The while loop continues to iterate as long as it has more elements, checked using hasNext. Within each iteration, next is called to move the iterator forward and return the current element, which is then printed. Comparison and sorting, comparable and comparator. In Java, the comparable and comparator interfaces are used for comparing and sorting objects. The comparable interface is used for natural ordering of objects and must be implemented by the class whose instances need to be sorted. The comparator interface is used to create different sorting sequences and can be passed to a sort method such as collections.sort or arrays.sort. In this example, we have a student class that implements the comparable interface and overrides the compareTo method to compare students based on their age. This allows objects of the student class to be naturally ordered by age when we use collections sort AL on an array list of students. The compareTo method returns a negative integer, 0, or a positive integer as this object is less than, equal to, or greater than the specified object. After sorting, students are printed in ascending order of their age. Basics of exceptions. In Java, an exception is an event that disrupts the normal flow of a program's instructions. It's an object which is thrown at runtime, indicating that an abnormal condition has occurred. Learning to handle these exceptions is critical for building robust applications. Let's start with a basic example that demonstrates how an unhandled exception can terminate a program. In the given code, we're attempting to access the 11th element, index 10, of an array that only contains 3 elements. Since array indices start at 0, valid indices for this array are 0, 1, and 2. Attempting to access myNumbers10 throws an array index out-of-bounds exception, leading to the termination of the program. This is a common example of an unhandled exception disrupting a program's flow. Learning to manage such exceptions is essential for writing error-tolerant code. Try, catch, finally blocks. In Java, exceptions are events that disrupt the normal flow of the program's instructions. Exception handling is crucial for robust applications. The try, catch, and finally blocks are used to handle exceptions. The try block encloses code that may throw an exception, while catch handles that exception. The finally block executes code after try and catch, regardless of whether an exception was thrown or not. In the given example, we enclose a risky operation, division by 0, within a try block. If this operation fails, it throws an arithmetic exception, which is then caught by the catch block. Regardless of whether the exception occurs or not, the finally block executes, ensuring that "this will always execute" is printed to the console. This structure allows safer execution of potentially harmful operations and guarantees some code will always run, useful for resource cleanup, like closing file streams or database connections. Multiple catch blocks and nested try. In Java, when exceptions are thrown, it's often essential to handle them differently based on the type of exception. Multiple catch blocks allow you to catch and handle various exceptions distinctly. Nested try blocks are used when a section of code may cause one exception, but within it, another section may cause a different exception. This structure enables precise and tidy handling of various potential problems. The code demonstrates the use of multiple catch blocks following a single try block. The try block contains a piece of code that attempts to access an invalid index of an array, which throws an array index out-of-bounds exception. The first catch block is for arithmetic exception, and would handle division by 0 errors, but since that's not the exception thrown here, it's bypassed. The second catch block catches the array index out-of-bounds exception and prints an error message. Lastly, there's a finally block that executes after the try and catch blocks, regardless of whether an exception was caught, ensuring the completion message is printed. This structure allows for handling different types of exceptions specifically and cleanly. Throws. In Java, throw and throws are mechanisms to handle exceptions. The throw keyword is used within a method to actually throw an exception, whereas throws is used in a method's declaration to indicate that this method might throw an exception, and it should be handled by the method that calls this method. In the provided code, the checkAge method throws an arithmetic exception if the age passed is less than 18, using the throw keyword. This is a way to manually trigger an exception based on a condition. The method's signature also includes throws arithmetic exception, indicating that it may throw an arithmetic exception, which needs to be handled by the caller. In the main method, the call to checkAge is wrapped in a try-catch block to handle the potential arithmetic exception. When checkAge 15 is called, the condition in the checkAge method evaluates to true. An arithmetic exception is thrown, and it's caught by the catch block in the main method, which then prints the message of the exception. Custom exceptions. In Java, while the standard exception classes can handle most common issues, sometimes you may need to create your own exceptions, known as custom exceptions, for specific error conditions. Custom exceptions provide a way to create specific error codes and error messages tailored to your application. In this code, myCustomException is our custom exception class that extends the exception class, allowing it to be used as an exception. The constructor of myCustomException takes a string message, which is passed to the superclass exception constructor. This message gets displayed when the exception is thrown. In the custom-exception demo class, inside the main method, we explicitly throw an instance of myCustomException with a custom message. The try block contains code that might throw an exception, while the catch block is used to catch and handle the exception defined. Upon catching the exception, we print out the message associated with it. This demonstrates how to define, throw, and catch custom exceptions in Java. Byte and character streams. Byte streams in Java are used to perform input and output of 8-bit bytes. They are very useful when dealing with binary data like images and audio files. Let's focus on using file input stream and file output stream to read from and write to a file respectively. In this example, we create a file input stream to read bytes from a file named input.txt and a file output stream to write bytes to a file named output.txt. We read 1 byte at a time from the input stream and write it to the output stream. This process continues until read returns -1, indicating the end of the file. The try with resources statement ensures that both streams are closed automatically. File handling, file input stream, file output stream, file reader, file writer. File handling in Java allows us to read from and write to files on the disk. File input stream and file output stream are used for reading from and writing to byte files, respectively. File reader and file writer are used for reading from and writing to character files. This distinction is important because text files contain characters, while binary files contain bytes. The code snippet is a scaffold for demonstrating Java's file handling capabilities. It imports the necessary classes but doesn't implement a specific file operation. In practice, you would use file input stream or file reader to read file content by creating an instance and calling methods like read to fetch data. Similarly, file output stream or file writer would be used to create a file if it doesn't exist or to write to a file by creating an instance and using write method. Each of these classes handles the data in bytes or characters respectively, catering to the type of the file you are dealing with. Buffered reader and buffered writer. In Java, buffered reader and buffered writer are character streams classes used to read and write data from and to a file efficiently. Here, we'll see a simple example demonstrating their usage. This code demonstrates writing a string, hello world, to a file named output.txt using buffered writer and then reading it back using buffered reader. The file writer and file reader classes are wrapped by buffered writer and buffered reader, respectively, to enhance efficiency. Buffered writer.write is used for writing data to the file, and buffered reader.readline is employed to read the data back. Both streams are closed after their operation ends, using the close method to release resources. Serialization and deserialization. Serialization in Java is a mechanism of converting the state of an object into a byte stream, which can then be persisted or transmitted. Deserialization is the reverse process, where the byte stream is used to recreate the actual Java object in memory. This is particularly useful in sending objects over a network or storing them in files. Let's go through a simple example to serialize and deserialize an object. In the example code, we define an employee class that implements serializable. It contains 3 fields, name, department, and age, with the age field marked as transient, indicating it should not be serialized. In the serialization example class, an employee object is created and serialized using an object output stream wrapped around a file output stream that writes to an employee.obj file. Then, we deserialize the object using an object input stream wrapped around a file input stream that reads from the same file. Note that during deserialization, the transient age field is not restored and defaults to 0. This process demonstrates how Java objects can be converted to a series of bytes and then reconstructed back into objects. Process and threads in Java. In Java, process refers to an executing instance of a program, including everything needed to run it: code, memory, resources, etc. A thread, on the other hand, is the smallest unit of execution within a process. Java uses threads to allow the JVM to execute multiple tasks at once. Here, we'll demonstrate basic thread creation by implementing the runnable interface. The code snippet creates a class that implements the runnable interface, which requires the definition of a run method. This method contains the code that will be executed by the thread. In the main method, we instantiate myRunnable, then create a thread object, passing the myRunnable instance. Starting the thread with myThread.start prompts the JVM to execute the run method in a separate execution path. This demonstrates the fundamental way threads are created and executed in Java, showcasing how tasks can be run concurrently within the same application process. Creating threads by extending thread class by implementing runnable interface. In Java, threads can be created by two main means, by extending the thread class or by implementing the runnable interface. Using the thread class is more straightforward but limits inheritance since Java supports single inheritance. Implementing the runnable interface is more flexible, allowing a class to inherit from another class while still being able to be run on a thread. In the example, myThread class extends the thread class and overrides the run method to define the thread's task. It's executed using the start method, which internally calls the run method. MyRunnable class implements the runnable interface and also defines the task in its run method. However, to start a thread using the runnable approach, you create a thread object, pass the runnable instance to its constructor, and then call the start method on the thread object. Both approaches will execute the tasks in separate threads when their start methods are called. Thread lifecycle. In Java, threads have a lifecycle that starts when an instance of the thread class is created and ends when the thread finishes execution. Understanding this lifecycle is crucial for managing threads effectively. The major states include new, runnable, blocked, waiting, timed waiting, and terminated. Let's see a simple example demonstrating how to create a thread and start it, which will cover some of these states implicitly. In the provided code, we define a myThread class that extends the thread class and overrides the run method, which contains the code that the thread executes. When an instance of myThread is created, it is in the new state. Calling the start method on this instance transitions it to the runnable state, at which point the Java virtual machine calls the run method to execute the thread's task. The thread automatically moves to the terminated state after the run method completes. This simple example doesn't explicitly showcase the blocked waiting or timed waiting states, but it demonstrates the basic transition from new to runnable, and finally to terminated within a thread's lifecycle. Thread priorities. In Java, each thread has a priority that affects how the thread is scheduled for execution. Priorities are represented by a number between 1 and 10, with 1 being the lowest priority and 10 the highest. The default priority is 5. Java provides a set of constants in the thread class for minimum, min priority, maximum, max priority, and normal, norm priority priorities. Setting a thread's priority can be useful for when you need to ensure certain tasks take precedence in execution over others. In the provided code, we modify the default priority of the main thread to the maximum priority using thread.currentThread, set priority thread.maxPriority. Then, we print its priority. When we create another thread, it inherits the default priority, 5 if not explicitly set differently. Upon starting another thread, it prints its priority. This example illustrates how thread priorities can be adjusted and queried in Java, where the main thread's priority is explicitly set to the highest possible value, while the newly created thread defaults to normal priority. Synchronization. In a multi-threaded environment, threads operate on shared resources, which can lead to data inconsistency. To avoid such issues, synchronization is used, which ensures that only one thread can access the resource at a time. Here, we'll illustrate how to implement synchronization in Java using a simple example of a counter. In the code, the counter class has a method increment marked with the synchronized keyword. This ensures that when one thread is executing this method, no other thread can execute it simultaneously, maintaining thread safety. We then create 2 threads in the main class, both of which call the increment method on the same counter object 1000 times. Without synchronization, both threads could access the increment method at the same time, possibly leading to less than 2000 as the final count due to data inconsistency. With synchronization, we ensure that the count variable accurately reflects the total number of increments performed by both threads, effectively preventing data race conditions. Inter-thread communication. Inter-thread communication in Java allows synchronized threads to interact with each other. This is essential in scenarios where threads have to coordinate their operations, such as when one thread produces data and another consumes it. Java provides wait, notify, and notify all methods for this purpose, facilitating a smooth communication pattern among threads to ensure efficiency and avoid potential deadlock situations. In the provided code, the class shared serves as a simple example of inter-thread communication. The data field holds an integer value, initially set to -1. Two synchronized methods, setData and getData, are used for setting and getting the data value, respectively. SetData waits using wait if data is not -1, indicating that the data hasn't been consumed yet to avoid overwriting. Once data is consumed and set to -1, setData updates data with a new value and notifies, using notify, other waiting threads, possibly the one in getData. Conversely, getData waits if data is -1, indicating no new data is available. Once data is available, it retrieves the value, resets data to -1, indicating the data has been consumed, and notifies other threads that may be waiting to set new data. This pattern effectively manages data exchange between producing and consuming threads, ensuring that data integrity is maintained through synchronization. Deadlock. In Java, a deadlock is a situation where two or more threads are blocked forever, each waiting for the others to release a resource they hold. Deadlocks can occur in Java when the synchronized keyword causes the executing threads to wait infinitely. The following code demonstrates a simple deadlock scenario. In this code, Class A and Class B both have synchronized methods that call each other. The main thread creates a new thread and starts it, then calls a.method A B. Inside method A, there's a call to b.last, which requires a lock on object B. Simultaneously, the new thread calls b.method BA, which includes a call to a.last, requiring a lock on object A. However, each thread holds a lock on one object and waits for the lock on the other, creating a deadlock. Neither finishes execution, demonstrating why it's crucial to avoid circular dependencies among synchronized blocks. Executor framework. The executor framework is part of the java.util.concurrent package, introduced in Java 5, to simplify the execution of tasks in asynchronous mode. It provides a higher-level replacement for working directly with thread objects, offering a flexible thread pool mechanism and simplifying task management. The following example demonstrates how to use the executor framework to execute a simple task. In this code, we start by importing the necessary classes from the java.util.concurrent package. We then create a class, executorDemo, with a main method to demonstrate the executor framework. Inside the main method, we initialize an executor service using executors.newSingleThreadExecutor, which creates a single-threaded executor. We define a runnable task that prints the name of the thread executing it. This task is submitted to the executor using executor.executeTask. Finally, executor.shutdown is called to stop the executor once it finishes executing the submitted tasks. This approach simplifies managing individual threads, especially when dealing with a large number of asynchronous tasks. Basics of networking. Networking in Java allows for the transmission and reception of data between two or more interconnected devices. At its core, Java networking revolves around the concept of sockets. A socket represents an endpoint for communication between two machines. Java utilizes the java.net package to facilitate network operations. Here we'll explore how to create a simple client-server application where a client sends a message to a server, which then echoes it back. In the provided code, we've established a simple server, Echo Server, that listens for connections on port 33333 using a server socket. Upon a client connecting, the server accepts the connection, resulting in a socket instance that facilitates communication between the server and the client. With the client connected, the server creates input buffered reader and output print writer streams to receive and send data, respectively. It then enters a loop where it reads a line of text from the client and echoes it back using the output stream. This cycle continues until the client stops sending data. Inner address class. The inner address class in Java is part of the java.net package. It's used for handling Internet Protocol IP addresses, both IPv4 and IPv6. It provides methods to get the local host address, check if an address is reachable, and retrieve the IP address or hostname of a specified URL or server, among others. It's a crucial class for network programming in Java. Now, let's see a simple example of how to use inetAddress to retrieve the IP address of a hostname. In this code, we import the Java net package to use the inetAddress class. We create a class named getIP with a main method that attempts to retrieve the IP address of www.example.com. The inetAddress.getByName string host method is used, which takes a hostname as a parameter and returns an inetAddress object representing the IP address of the host. We then call getHostAddress on the resulting inetAddress object to print out the IP address. If the hostname is not found, which means it cannot resolve to an address, the catch block captures the unknown host exception and prints an error message. URL connection, HTTP URL connection. In Java, the URL class is used to represent a URL, which is a pointer to a resource on the web. A URL can be broken down into parts such as protocol, host, port, and file. This example shows how to create a URL object and then extract various components from it. This code creates a new URL object pointing to a given web address. The URL class provides methods to retrieve different parts of the URL. GetProtocol returns the ProTP. GetHost returns the domain name www.example.com. GetPort returns the port 80, which is default for HTTP. GetFile returns the file path on the /docsbooks tutorial/index.html networking. And GetRef returns the reference part of the URL. Sockets and server sockets. In Java networking, the concept of sockets and server sockets is fundamental for building networked applications. A socket is one endpoint of a two-way communication link between two programs running on the network. A server socket, on the other hand, is used on the server side to listen for incoming connection requests from clients. This code snippet demonstrates the creation of a simple server using Java's server socket class. The constructor of server socket takes a port number, 5000 in this case, that the server will listen on for incoming connections. The server starts by printing server started to the console. It then calls the accept method, which waits for a client to connect. Upon a successful connection, client connected is printed to the console. The server then gets the input stream from the socket to read data sent by the client. Here, the server reads a line of text sent from the client and prints it. Finally, the server socket is closed. This is a simple example demonstrating server-side socket programming. Client-server programming. In Java, client-server programming is a fundamental concept where two types of programs communicate over a network. The server program listens for requests from clients, processes them, and sends responses back. The client program sends requests to the server and receives responses. Here, we'll create a basic server that listens for connections on port 1234 and a client that connects to this server. Both will exchange a simple message. The server.java creates a server that listens on port 1234. It uses a server socket to listen for incoming connections and accepts them with server socket.accept. When a connection is established, it reads a line from the client, prints it, and replies with a message. The client.java code establishes a connection to the server running on localhost at port 1234. It sends a greeting message to the server, waits for a reply, and prints the server's message. Both the client and server use PrintWriter for sending messages and buffered reader for receiving messages. After the exchange, both close their connections. Lambda expressions. A lambda expression is a short block of code which takes in parameters and returns a value. Lambda expressions are similar to methods, but they do not need a name and can be implemented right in the body of a method. In the code snippet, we create a list of string objects named namesList, containing 3 names. Using the forEach method, which iterates over each element of the list, we pass a lambda expression as its parameter. This lambda expression is indicated by the arrow operator. It takes a single parameter, name, which represents each item in the list, and prints it out. The expression simplifies the use of an anonymous class for implementing the interface required by forEach, making the code more concise and readable. Stream API. The Stream API introduced in Java 8 provides a modern, efficient way to process sequences of elements, including those in collections. It supports various operations that can be pipelined to produce the desired result without modifying the underlying data source. Operations are either intermediate, returning a stream, or terminal, producing a result or side effect. Here's a simple example demonstrating how to filter, sort, and print a list of names using Stream API. In this code, a list of names is created using arrays.asList. The stream method is called on this list to initiate the stream operations. First, filter is used to select only those names that start with T. Next, sorted arranges the remaining names in natural, alphabetical order. Finally, collectors.toList is a terminal operation that gathers the filtered and sorted names into a new list. The result, which is a list containing Tanya, is printed to the console. This example demonstrates the chaining capability of stream operations and how they can be used to concisely process collections. Functional interfaces. In Java 8, a functional interface is an interface with just one abstract method, excluding the methods from object class, but it can have multiple default or static methods. These interfaces are intended to be used primarily with Lambda expressions. The functional interface annotation is not required but is helpful for the compiler to generate an error if the annotated interface does not satisfy the conditions of a functional interface. In the provided code, greet is defined as a functional interface with a single abstract method, say hello, which takes a string argument and returns nothing, void. We use the @functional interface annotation to explicitly declare it a functional interface. In the main method, we create an instance of the greet interface using a Lambda expression, name system.out.println hello name. Here, the Lambda expression implements the sayHello method. Finally, we call the sayHello method with world as an argument, using the greeting instance, which results in printing hello world to the console. Default methods. In Java 8, a new feature called default methods was introduced to interfaces. This allows you to define methods within an interface that have an implementation. Prior to this, interfaces could only contain method declarations. The default methods enable interfaces to evolve without breaking the existing implementations of these interfaces. In the code example, we have an interface named vehicle with a default method named print. This method prints a simple message to the console. The car class implements the vehicle interface but does not provide its own implementation of the print method. When we create an instance of car and call the print method, the default implementation provided in the vehicle interface is executed. This demonstrates how default methods can be used to provide a common implementation that can be shared across all implementers of the interface. Time API. Java 8 introduced a new time API under the java.time package. This comprehensive API is designed to overcome issues with the old java.util.date and java.util calendar by providing immutable classes and a clearer API for dates, times, durations, and periods. Let's explore how you can create and manipulate dates using the new API. In this code, we first import the necessary classes from the java.time package. We then create a local date object representing April 15th, 2023, using the of method. Similarly, a local time object for 13/4/5/20 is created. Combining these, we create a local date time object representing both the date and time. Finally, we print each object to the console. This demonstrates how you can work with dates and times separately or together and highlights the immutability and thread safety of the new API classes. Garbage collection. In Java, garbage collection is the process of automatically freeing memory on the heap by deleting objects that are no longer accessible in your program. Java provides a garbage collector to automate this process, so developers do not need to manually free memory, reducing the risk of memory leaks. However, understanding how and when garbage collection occurs can help you write more efficient Java programs. In this code snippet, a new string object containing hello is created and assigned to the variable star. Later, star is reassigned to null, making the previously created string object unreachable and eligible for garbage collection. Calling system.gc is a way to suggest that the Java Virtual Machine (JVM) performs garbage collection, although it's not guaranteed the garbage collector will run immediately. This example demonstrates how objects become eligible for garbage collection and the manual request to the garbage collector, highlighting the automated memory management in Java. Annotations. In Java, annotations are a form of metadata that provide data about a program but are not part of the program itself. Annotations have no direct effect on the operation of the code they annotate. However, they can be used by the compiler or at runtime by various tools and frameworks. In this code snippet, the @override annotation is used. This is a marker annotation indicating that the method toString is intended to override a method in a superclass. While not strictly necessary for the Java compiler, which can override methods without this annotation, it's a best practice to use @override for two reasons. First, it makes your intentions clear to anyone reading the code. Second, the compiler will generate an error if the annotated method doesn't actually override a method in its superclass, helping to catch potential bugs early in the development process. Reflection. Reflection in Java allows an executing program to examine or introspect upon itself and manipulate internal properties of the program. It is mainly used for debugging and testing purposes, as well as for the dynamic discovery of program components. For instance, reflection can be used to retrieve information about classes, interfaces, fields, and methods at runtime without knowing the names of these components beforehand. The code demonstrates basic usage of Java reflection to list all declared methods of the java.util ArrayList class. It starts by obtaining the class object representing ArrayList using class.forName java.util.ArrayList. This is essential for reflection as it serves as the entry point to the reflection API. Subsequently, it invokes getDeclared methods on this class object to fetch an array of method objects representing all the methods declared in the class, including public, protected, default, package, access, and private methods, but excluding inherited methods. For each method object, it prints out the method name using method.getName. This showcases how reflection can dynamically inspect and interact with class components. Java generics. Java generics enable types, classes, and interfaces to be parameters when defining classes, interfaces, and methods. Much like the more familiar formal parameters used in method declarations, type parameters provide a way for you to reuse the same code with different inputs. The benefit is robustness and readability of your Java code. In this code snippet, we've defined a generic class named box with a single type parameter t. This t can be any class or interface type. The class contains a private variable of type t and methods to set and get this variable. Because t is generic, you can create a box object to store any type of object. For example, creating an instance box integer will allow box to store an integer, and using box string would allow it to store a string. This approach provides compile time type safety and eliminates the need for typecasting that was necessary before generics were introduced in Java. Concurrency utilities. In Java, concurrency utilities are part of the java.util.concurrent package, providing robust mechanisms for managing and synchronizing execution of threads. It significantly simplifies development of multi-threaded applications. Let's look at a core example using executor service to run tasks in an asynchronous manner. This example initializes an executor service with a single thread. It then submits a simple task to the executor, which prints a message to the console. The task is an example of a lambda expression, representing a simple, parameterless function that's executed by the thread. After submitting the task, the executor is shut down with executor.shutdown, ensuring that it stops accepting new tasks and completes the execution of existing tasks. This demonstrates the ease of running tasks asynchronously and managing thread life cycles with concurrency utilities. Java Module System. The Java Module System, introduced in Java 9, brought about a significant change in how Java applications are organized and modularized. It allows developers to encapsulate and organize code in a more robust manner. A module is a named, self-describing collection of code and data. The system's primary goal is to improve the scalability and maintainability of Java applications. Here's a simple example to illustrate module definition and usage. The module info.java file defines a module. In this example, the module's name is com.example.module. It requires the java.school module, indicating dependencies. Additionally, it exports the com.example.module.api package, making it available to other modules. This structure allows for encapsulation of internal components and clear declaration of dependencies, thus facilitating better software architecture.